Welcome back, my dear student friends. Welcome back to our channel. Today we are going to see the typical root locus standard diagrams. So for the standard transfer functions, what are the standard shapes of root locus diagram? See, let's start with the first order system. See, a first order system is a standard. Okay, standard RLD diagrams. Okay, standard, typical, or typical RLD diagram. Let us consider a G of S. Okay, G of S, H of S equal to K by 1 plus S tau. Okay, 1 plus S tau 1. Okay, or 1 plus S tau. So how many poles are here? So one pole, only one pole at S equal to 1 by tau minus 1 by tau. So one pole is there is no zero. So what is the root locus? So root locus branch of the RLD starts at S equal to minus 1 by tau, and branch RLD branch starts at S equal to minus 1 by tau and terminates at, this is at the gate K equal to 0, terminates at infinity. Okay, terminates at infinity with the K values infinity. Understand or not? So let us draw the pole zero plot for this diagram. So one pole at 1 equal to minus 1 by tau. So the branch starts from here. Understand? So it ends at K equal to infinity somewhere. Okay. So this is the when K here K equal to 0. So this is a typical root locus plot for this system. Okay. Then let us continue. Clear? So this is the typical plot for this transfer function, K by 1 plus S tau. Right? Next, say G of S, H of S equal to G of S, H of S equal to K by second order system 1 plus S tau 1, 1 plus S tau 2. How many poles are there? 2 poles are there. So one pole P1 is at minus 1 by tau 1, P2 at minus 1 by tau 2. Okay, so what is the typical plot for this? So 2 poles in the negative real axis, minus 1, minus 1 by tau. Okay, minus tau 1, tau 2. Take tau 1 is greater, tau 1 and tau. Now see, if you stand here, no poles. If you stand and look into the right hand side, so there will be a pole between these two, right? So 2 poles are there. So definitely, see here, one pole originate from this and one pole originate from this. So they will break away, take a breakaway point. The breakaway point is similar to this. If you calculate the breakaway point and the angle of asymptotes, both are 90 degrees, right? So breakaway point and the angle of asymptotes 90 degree. So one pole K equal to 0. Here also K equal to 0. This branch this direction, this branch this direction. This branch ends at K equal to infinity. Here also it ends at K equal to infinity. Understand? So this is the typical plot. The angle of asymptotes is 90 degree, right? Asymptotes are 90 degree. So this is for the typical root locus diagram for the second order system. Understand or not? So if a third order system, so G of S, H of S, G of S, H of S equal to, you add one more factor, okay? So 1 plus S tau 1, 1 plus S tau 2, 1 plus S tau 3. So if you add one more factor, what is the shape, right? Let us see the diagram. So this is minus 1 by, say, this is minus 1 by tau 1. Another 3 poles are there, minus 1 by tau 2, minus 1 by tau 3. Now see, you can tell me the standard root locus, where are the root branches lie. So we stay here and look into this side, no poles, sum of poles and zeros are there, not there. If you stand here, only 1, so it is an odd number. So definitely there will be a branch between these two poles. So you stand here, sum of poles and zeros, even number. So no poles here. If you stand here, 3 poles are there, definitely a branch lie here in the root locus diagram. Okay. So then this pole, this branch, in this branch, there are how many poles? 3 poles. How many branches? 3 branches. Okay. How many branches terminate at 0? No. 0 branches. Okay. No zeros, right? 0 branches terminate. Okay. Terminate at 0. Okay. Infinite 0. So all the 3 branches terminate at infinity. Okay. So all the branches originates from the poles and terminates at infinity. Okay. So this branch moves this direction, from this moves this direction, then take a break away here. So there is a break away point. So where break away points available? When 2 poles are neighbor to each other, 2 poles between the branch between 2 poles, then there will be break away. When the branch between 2 zeros, then there will be a break in point, right? So break in point. Understand? So the typical breakaway, break in, the angle of asymptotes are similar to this. Understand? So since these two are similar, so this is the angle of departure. Okay. Sorry, sigma, real part and the imaginaries. So this is the typical plot for. So this, the third branch starts here at k equal to 0. Here also k equal to 0. Here also k equal to 0. So this branch terminates at k equal to infinity. This branch also terminates at k equal to infinity. Understand or not? So this is the typical plot for third order system. Third order system. Understand? Any doubt? Third order system. Next, if the G of S, H of S is there, if G of S, H of S is K by S, an integrator. So how many poles? One pole at S equal to 0 at the origin. So what is the diagram? So the typical the pole only at here. So if you stay here and look into the back, the odd in number, so the branch is available here. So one pole originates from here and end at infinity since there is no zeros. So here k equal to 0, here k equal to infinity. Okay, this is the typical root locus diagram. Okay, j omega real pole. Right. Next, if we add one more integrator in the first order system, it becomes second order g of s h of s equal to k by s into 1 plus s tau 1, 1 plus s tau 1. So here two poles. So two poles, one pole at s equal to 0, another pole at s equal to minus 1 by tau. So what is the pole? Okay, what is the root locus diagram? So one pole at s equal to 0, another pole at s equal to minus 1 by tau. Okay, minus 1 by tau 1. So the branch between these two are available. Okay, so the branch between these two are available. So one branch moves towards this direction, another branch moves towards direction. So they take break away. So two branches take away in this sense. Okay, so this is break away point. Break away point. Understand? So this is j omega sigma. So this is a typical plot for this. Next, if g of s h of s, if g of s h of s equal to, we'll add one more factor with this, s into 1 plus s tau 1, 1 plus s tau 2. So what happened to the root locus diagram for this plot? Okay, so very simple. There are three poles. You draw here. There are three poles. Move to next color. So one pole at origin. So one pole at origin, s equal to 0. So one pole at sorry, one pole at s equal to minus 1 by tau. Another one is minus 1 by tau 2. Okay, so between these two poles at 0 and tau 2, there will be a branch. There will be a branch. Okay, since the right side is odd number. So here there is no branch. So, but here the branch is available. So k equal to 0. The one branch start from here and end at k equal to infinity. Here from here k equal to 0. Here also k equal to 0. K equal to 0. Here k equal to infinity somewhere here. So k equal to infinity. So there is no branch here. So this branch, this branch starts. This branch minus 1 by tau 2. One branch moves this direction. Another branch moves this direction. So they take break away here, somewhere here. So what is the shape? So there are two angle of asymptotes available here. So two angle of asymptotes. This is the typical shape for these two poles. K equal to 0, the end at k equal to infinity. So here k equal to infinity. So two branches. So totally three branches. Understand or not? So next is if you have one factor in the numerator, what is the shape? So g of s h of s equal to k 1 plus s tau is at 0. Okay, s into 1 plus s tau 1, 1 plus s tau 2. Understand? So what is the shape? So there are three poles. So three branches. So 1, 0. So remember, among three branches, one branch terminate at 0 because 1 0 is available. Another two branches terminate at infinity, very high gain, k equal to infinity. We don't know the actual. So what is the shape? the shape of the shape, right? So one pole at s equal to 0, one pole at s equal to minus 1 by tau 1, another pole at s equal to say you have a 0 here, so 1 0 here, assume 1 0 between this, then here one more pole 1 by tau 2. Okay, this is minus 1 by tau z 0, right? So now where the branches are available. So between these two poles, there are two branches. There are two branches. Clear? Two branches. One branch start from here, another branch start from here. So here no branches. Here branches are available. So here one pole is there. So here branch available. So this is 0. So one branch starts from k equal to 0 from minus 1 by tau and end at this 0. End at this 0. Am I right or wrong? So end at this 0. So this branch, one branch terminates at 0. So k equal to, at 0, k equal to infinity. So this branch moves this direction. This branch moves in this direction. They take away a break, right? So what is the shape? So the shape of the root locus diagram is like this. So this also ends at infinity. This also ends at infinity. We don't know. It is at the finite state. So this branch starts at k equal to 0 here. This branch also k equal to 0. So this is imaginary axis. This is real axis. So this is the typical plot for this transfer function, right? Suppose if the transfer the root, if multiple roots at the origin, say g of s, h of s equal to k by s square, right? K by s square. So poles, two poles at s equal to 0. Okay, two poles. Okay. So how many branches? Two branches. Branches are two branches. So no zeros. So both branches terminate at infinity. Okay. So what is the typical plot for this? Okay. So both poles are at s equal to 0. So it approaches towards the imaginary axis. At India, so this is the one branch. This branch starts at k equal to 0 here and end at k equal to infinity. This branch starts from here and end at k equal to infinity. This is the typical plot for this transfer function, this integrator, double integrator, right? Understand or not? Yes. Next, if the transfer function is g of s h of s, g of s h of s equal to k by double integrator. We add double integrator with this 1 by s tau 1. So what is that? There are three poles, no zeros. So three branches, all three branches terminate at infinity. Understand? So what is the shape? Okay, the shape of this RLD diagram for this j omega. This is real. So two poles at the origin. So one pole at minus 1 by tau. Can you tell me what is the where are the branches are available? See, where are the branches available? Two poles at origin here. So if you see, look into here, there are two poles. So even in number, so no branch here. If you stand here, see, look here, look back to the right side. So if you look back to the right side, so there are three poles. Okay, 3 poles. So odd number. So here one branch. So this branch originates from this pole at k equal to 0 and terminate at k equal to infinity. So these two poles, okay, starts from here and ends at infinity. So you know the shape of this, so like a parabola. So the shape will be like this. So this branch moves and k equal to ends at k equal to infinity. This branch terminates at k equal to infinity. Here both k equal to 0, originate at k equal to 0. Understand? So this is the typical plot for root locus, right? For this transfer function. Next, g of s, h of s equal to k into 1 plus s tau z divided by 2 integrators and 0 in the numerator, s tau 1. So how many poles? 3 poles, 3 branches, 1 0. So one branch terminate at 0, terminate at 0. 2 branches terminate at infinity, not the zeros. Let us see the diagram, root locus diagram. Okay, so 2 poles at s equal to 0, another pole minus 1 by tau 1, s is at 0 at minus 1 by tau z, right? So 1 0 minus 1 by tau z. So 1 pole minus 1 by tau 1, 2 zeros here, 2 zeros here. So what is the root locus? So you stay here, you stand here and look back this side, 2 poles are there. So no branch here. If you stand here, look here, 2 poles and 1 zeros. So odd in number. So there will be a branch between these two. So this branch originates at k equal to 0 from the pole and end on the 0 k equal to infinity. Okay, understand or not? So these two are there. So here 2 branches are here. So 2 are approaching infinity. So what is the shape of the diagram? So this is the typical shape of the root locus diagram for this transfer function. So k equal to terminate at k equal to infinity, originate at this s equal to 0. Okay, s equal to 0, k equal to 0 here. These two, there are 3 branches, right? Understand? Okay. Next transfer function is g of s, h of s, right? K into 1 plus s tau z divided by third order. Okay. So poles, number of poles 3, branches 3, one branch terminate at 0 minus 1 by tau z, 2 branches terminate at infinity. Understand? So what is the shape for this plot, this root locus, this factor? Okay. So one pole, 1 0 minus 1 by tau is that 1 0. There are three zeros at s equal to 0. 3 zeros. Understand? So j omega, this is real. So what is the shape? You see, let us examine the number of poles and zeros. If you stand here, look into this. There are three 3 poles here. So there will be a branch between this and this. So origin, from origin and this pole. So from among three, one branch originates from this among these 3 pole and terminate at infinity here. So one pole, one branch k equal to 0, k equal to infinity. So remaining 2 branches terminate at somewhere here. So you know the shape of the branch. Okay. So from here, k equal to 0, one branch starts and end at k equal to infinity here. This branch starts k equal to 0 at origin and end at k equal to infinity in this diagram. So these are all the various typical RLDs, root locus diagrams. Please remember these standard shapes. Based on that, many question will be asked in the gate examination. Okay, understand? So thank you very much for your kind observation. Happy learning. Okay, please don't forget to subscribe our channel. Thank you very much.